look like? None of these? No? Happy memories, huh? Happy memories. Good times. All right. What were we doing last time? Oh, that's right. We were using truth tables, those wonderful things, truth tables, to test whether or not propositions are logically equivalent. So, just to make sure you remember how, tell me, well, work this out, whether or not these are logically equivalent. Yeah, that should keep you busy. How many rows are you going to need? What? 16. What? How do you know? Because there's 4 letters and it's 2 to the power of however many letters there are. As for your sickies, should quarantine you all. You threatened to sue me like that nurse in Maine. All right, now remember how to do the truth values. You alternate this one, true, false, true, false. You double it for this one, true, true, false, false. Oops, got it wrong already. And then you double it again, true, 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 true. And then finally, this is going to be 8 trues, 4, 5, 6, 7, 8, and 8 falses. 1, 2, 5, 6, 7, 8. That way you'll get every single possible combination without having to think about it. You could probably pause the video. This is not gripping viewing. Exactly the same. Should I repeat that? No, that's okay. Yeah, so this is good practice anyway because you've had to work out the truth value of this whole thing for lots of different combinations of truth values. It's good to get practiced at that. And you've had to work out the truth value of this whole long proposition. The truth value, the main connective will be the ampersand, but then you have to work out the truth value of each of these before you can work it out. It's good to make you suffer. It makes you stronger in the end. All right, so that's using truth tables to test whether or not propositions are logically equivalent. what else can we do with these wonderful things called truth tables? Turns out, one very important thing you can do with truth tables is use them to test arguments for validity. This is perhaps the most fundamental thing that we're concerned with in this class. This class is logic. Logic is concerned with logical reasoning, with giving arguments, and the arguments that work deductively are called valid arguments. So if we can use truth tables to provide an infallible test of validity, that would be a very good thing. We've already seen other tests for validity. What specific test do you remember from the midterm? Venn diagrams, yes. Venn diagram was a test for validity, which was great as far as it went, but it had its limitations because it only works on a certain kind of argument. What kind of argument? A categorical syllogism. So it has to be A, categorical, and B, a syllogism, just two premises and a conclusion. It would be nice if we had a test for validity that worked on a wider range of arguments. And we do. It's the truth table test. Okay. So how does the truth table test work? Well, first of all, we need to remind ourselves, especially as many of you didn't do too well on this part of the test, on the definition of validity. Remember, validity is a feature of arguments. A valid argument is a logically good one, to put it vaguely. Why do people give arguments? People give arguments all the time. They give arguments to try and convince people of things. They try to convince people of their conclusions by showing that the conclusions, in some sense, follow from the premises. When this works, you have a valid argument. So what is an intuitive definition of validity?
When the premises guarantee the conclusion.
When the premises guarantee the conclusion. Now, what does it mean to say they guarantee it? You know, is it a law of physics or something? No. So what logicians decided is that you could characterize guaranteeing in terms of truth values. So the truth value based test for when an argument is valid is, and you might want to write this down, an argument is valid if the premises are true, the conclusion has to be true. In fact, an argument is valid if and only if the premises are true, the conclusion has to be true. So here we have a characterization of guaranteeing in terms of truth values. In other words, if the premises are true, the conclusion had to be true. And we saw why this was the case with Venn diagrams. Because we saw in Venn diagrams, the information in the conclusion of a valid argument was contained within the premises. So if the premises are true, in some sense the conclusion is automatically made true because the information is already there in the true premises. So making the premises true made the conclusion true already. Okay, so that's the truth value based test for validity. Now, that's the idea behind using a truth table to test for validity. So, let's consider two arguments. Here they are. What's this one called? Affirming the antecedent, also known as modus ponens. What's this one called? Affirming the consequent. One of them is valid, the other one is not. Which one is valid? The first one, affirming the antecedent. This one is not. Okay, now we've already talked about this, and I've used examples to try and illustrate this. let's prove it now that that one is valid and the other one isn't. So let's start with the invalid one. So we're going to prove that this is invalid using a truth table. What does the truth table look like? Well, guess how many rows it's going to need? 4 rows. Why? Because there's only 2 different letters involved. So, and also we're going to need a column for each of those letters. P, Q. Remember what I called this part of the truth table? No, not sneeze. What's that?
Scaffolding.
Scaffolding, that's right. This is, I call this a scaffolding because basically it's something that enables you to construct your finished truth table, but isn't really part of the truth table. So, but you can set that up without even really thinking, although probably you should think when you're constructing actual scaffolding, otherwise there'll be workplace accidents. Alright, so it's going to look like this. And I'm going to draw a double line to separate it from the actual part of the truth table that we're going to care about at the end. Now what's that going to look like? Well, it's going to be 3 columns. 1 for each premise and 1 for the conclusion. So the first premise is if P then Q, draw a line. Second premise is Q. Then I'm going to draw another double line because there's an important distinction between the premise and the conclusion, as we'll see. Okay. Now, fill out that truth table. In other words, work out the truth values for each of these. Yes, you. I'm doing a poor job with it. Row. True, true, true. True premises and a true conclusion. Huh. Remember the definition of validity. The definition of validity was if the premises are true, the conclusion has to be true. Does this row prove that this argument is in fact valid? Spoiler alert. No, it doesn't. Because this is an invalid argument.
Must
So,
prove that it is not.
what's that?
If row 1 would prove that it is valid, then row 3 must prove that it is not.
Yes, in fact, row 3 is the important row. But let's go back to row 1 for a second. Here's the reason why that row does not prove that it's a valid argument. Because remember, the definition of validity is not the premises and the conclusion can be true together. It's the premises guarantee the conclusion. So why doesn't this show that the premises guarantee the conclusion? Well, think of this argument. Premise 1. Today is Wednesday. I'll use W for that. Premise 2. Whales are mammals. I'll use M for mammals. Conclusion. The Royals won last night. Is that a good argument? Is it a good argument? Why not? Because there's no way that those premises support that conclusion. Because to support a conclusion, you'd think they must at least be relevant, right? But there's no relevance. These are totally unconnected things. However, notice something about each of those. What is true about all 3 of these?
They are all in fact the case.
They are true. This is true, and this is true. Just like here. So, in other words, what I'm illustrating is it's possible for the premises and the conclusion to be true together, without it proving that it's a valid argument, because this is clearly not a valid argument. How do we know it's not a valid argument? Answer, because it's possible for them all to be true together, but it's also possible for these to be true and this to be false. Next week it will be Wednesday. Next week Wales will still be mammals, but the Royals will not have won the night before. So merely having a line like this does not prove the argument is valid. It just proves that it's possible for all the premises and the conclusion to be true at the same time. That's not enough. So what proves that it's invalid is, as Donna's already said, row 3. Why does row 3 prove that it's invalid, not you?
Because both premises are true and the conclusion's false.
So what?
Well, in the top one, both of them are true and the conclusion's true, so you're getting conflicting.
No, actually, it doesn't even matter. Even if you didn't have that row there, this would still prove it. So it's not the conflict that's the problem.
Because if both of the premises are true, then it has to be.
Yes, because if the premises guarantee the conclusion, then it should be impossible for this to happen. Clearly it's possible because there it is. So if it's possible, what this shows is that it's possible for the premises to be true at the same time the conclusion is false. In a valid argument, that is not possible because the premises guarantee the conclusion. So, in effect, the truth table method is a test for invalidity. Because what you're looking for is a line where all the, in this case, there are only 2 premises, but there can be 30 premises. I wouldn't do that to you, but it's possible. In that case, all of the premises have to be true at the same time, and the conclusion has to be false. If that is possible, and if it's possible, it'll be a line in your truth table, because remember, this truth table covers all possibilities, because it's only possible for P to be true or false, and there's only 4 possible combinations. So this covers all possibilities in the universe for this argument. If it's possible, it'll be one of these rows. And yes, it is. It is possible for the premises to be true and the conclusion to be false. That proves that this argument is invalid. Okay? All right, so the truth table test for validity is in fact a truth table test for invalidity. You're looking for a row where all the premises are true and the conclusion is false. And if you find it, it proves invalidity. Okay? Now, let's try it with modus ponens, which we know is valid. I'm going to be lazy. You should just redraw the entire table. But I'm going to take a shortcut. Okay, so we're going to pretend that wasn't a premise, and we're going to pretend that this is a premise and that this is the conclusion. So premise 1, premise 2, conclusion. Again, we're going to cover up the scaffolding now because we don't need it. Now, this argument is valid. Is it valid because of this line? What's that? Is it valid because of this line? Yes or no? No. How do you know? Because we had exactly that line with an invalid argument. So if it's possible with an invalid argument, then that line cannot prove validity, right? Okay. So what about this table proves that the argument is valid?
It's not invalid.
Yes. It proves that it's valid because it's not invalid. In other words, to prove that an argument is valid, you've got to not find something. What have you got to not find? Where the premises are all true and the conclusion is false. So how many rows prove that an argument is invalid?
Just one.
Just one. So in other words, if you draw a table and you find on the first row true, true, false, you're done. The argument is invalid. You don't have to fill in any more unless I ask you to on your homework. Right? But in effect, you already know that it's invalid. However, if it's not true, true, false on the first line, or on the second, or on the third, you have to keep going until either you find the line or you finish the entire table. If you find the line, it's invalid. If you finish the entire table and you don't find the line anywhere, that's the only way to prove that it's valid. So you prove it's valid by proving that it's not invalid. In other words, by not finding the invalid line. So there's no line where it goes true, true, false. Every time the conclusion is false, one of the premises is false. Every time the premises are all true, the conclusion is also true. You never get true, true, false. Yes?
So the only time it's invalid is true, true, false?
Well, or, depending on how many premises. If you have 30 premises, it will be true 30 times false. Okay? Now, before we do some exercises, which we're going to do, I'm going to show you one little dirty secret about logic. One little oddity. Remember, we are working from a kind of intuitive concept of validity. An argument is valid if the premises guarantee the conclusion. And logicians come along and say, I can characterize guaranteeing in terms of this test, the truth table test. So therefore, this is a test for validity. And in the vast majority of cases, it works. It matches up. We know that these premises guarantee this conclusion, and look, this proves it. The trouble is, there's a couple of cases where something weird happens, and this test says the argument is valid, when intuitively we would say that it isn't. Let me give you an example. Consider this argument. Here's the premise. It's Wednesday, and it's not Wednesday. Therefore, whales are mammals. Is that a valid argument? Do you think the premise guarantees the conclusion? No. Why not? Because the premise has nothing to do with the conclusion. How can it guarantee if it has nothing to do with it? Well, do the truth table test for that argument. All right, who's finished the table? All right, we'll keep going until the rest of you finished it. And it should look like that. And once again, we can cover up the scaffolding because it's not relevant. What's weird about this?
That's invalid.
Yeah. What are we looking for? What's the test for validity? We look for something. What do we look for? True premise is a false conclusion. In this case, it's premise singular because it's a one-premise argument. You can have one-premise arguments. They're just not as common as syllogisms. Well, this one's one. So we're looking for a line where the premise is true and the conclusion is false. Do we find that line? No. So this argument is valid. Huh. That's a little weird. Why is it valid? Well, because it's not invalid. And why? But what's the kind of cheating reason why it's not invalid? Because, don't click your notes. Because this is what's called a logical contradiction. What does that mean? It's never true. It's not just false in one circumstance, it's false in every single circumstance. It's what's called necessarily false. There's no way that it could be true. So of course there's no case where the premises are true and the conclusion is false, because there's no place where the premise can be true. But that doesn't seem to mean that it's a valid argument, certainly not in our intuitive sense. Because it doesn't intuitively seem right to say that, it's Wednesday and it's not Wednesday, therefore whales are mammals. In fact, does it matter what the conclusion is? No, the conclusion could be anything you like and it would still be a valid argument. So in logic, we express this by saying you can derive anything from a contradiction. If your premise is a contradiction, then whatever your conclusion is, it's going to be a valid argument. Is it going to be a good argument? No. It's just a quirk of the truth test. There's one other kind of weird argument.
Sounds like garbage in, garbage out to me.
Yeah. There's another kind of weird argument that would do exactly the same thing. Only this time because of the conclusion. What would that be? Not when the conclusion is a contradiction.
Conclusion's always true.
When the conclusion is necessarily true. So in other words, an example of that would be P or not P. Why is that necessarily true?
It's always true.
Yes, why is it always true?
So if P is false, then not P is true. And
Yeah, because in a disjunction you only need one of them to be true, and that'll either happen because P is true, or if P is false, then not P will be true. So this is always going to be true in every possible circumstance. Why will anything that has that as the conclusion be a valid argument?
Because its conclusion is always true.
Yes, because you can never have
A false conclusion.
true premises and a false conclusion, because you can't have a false conclusion. So, you know, Elvis is alive, therefore today is Wednesday or it's not Wednesday. That's a valid argument. So that's a little weird. That's a case where the truth table test seems to veer a little bit away from what it's supposed to capture. But in all we allow logic that quirk because it's so useful and it works on every argument that intuitively is valid. And it also provides us some means for testing for validity very complicated arguments where we have no intuitions about whether it's valid or not. You know, suppose you had an argument with 20 premises. There's no way you could say, yeah, that's valid. You know, but you could test it using the truth table method. So it's useful. Turn to page 365, the number of days in a non-leap year. Nick, do you not have your book? You're just pondering deeply the nature of validity. Wrapped up in your thoughts. Okay, you don't have to do number 1 of practice quiz 13.1 because we've already done it. But you have to do all the others. So that includes over the page. And we can probably pause. No, I don't even need to know what this is. Yes, so now of course if I asked you in your homework to fill in every square, then you have to. But if I asked you work out whether or not this is valid, you would know by the time you reached here. Because provided you fill in all these, you know that once you've checked this one and this one, you know that there is no possibility of getting all true premises and a false conclusion. Okay. Number 6. Who have we reached? Jordan.
Valid?
You said what?
It was valid.
Valid. Okay. Who agrees? Yes, because where the conclusion is false, the premise is false. Where the premise is true, the conclusion is true. So there is no true-false combination. Are they logically equivalent? No. There's a difference here. So they're not logically equivalent. In fact, you could tell that that is a valid argument by De Morgan's law. We keep talking about De Morgan's law before we get to it. Eventually we'll get there. Pretty soon. Oh, that reminds me. I know that I've told my previous class, but I think I told them twice instead of telling them once and you once. I'm not going to be here next week. Did I tell you that? No. I know. I'll give you a moment to recover from your grief. But, however, maybe this will give you grief. We're not going to slow down. For a week, this is going to be an online class. Okay? So we're going to stick to the syllabus, except you don't have to show up here unless you want to see Eric. Are you going to show up? I mean, well, he won't bother showing up unless, you know, people email him, because I know you're free at this slot.
Yeah.
Yeah, you know, and he'll probably have his sessions the same as usual. But so there's going to be a homework, same as everything, and I am going to put little videos on the material, which let's see, yes, November 3 and November 5th. So I'm going to put little videos that cover this material on Blackboard. They're going to probably be fairly crappy quality because it'll be off my laptop from a cafe in Prague, so I'll be enjoying myself. Yeah, so we will cover this material despite me not being here. Just so you know. So if you show up bleary-eyed next Monday and the room is empty, now you know why. But yes, once again, there will be a homework, as usual. So it will be as if I'm here, only I won't be here. Good, now I've told you. All right. What about this one? Once again, it's an 8-liner. Boy, I'm running out. Samantha, where is this line? This row used to be packed. You've driven them all away. It's valid. Once again, I could be lazy and I could just do this one and notice that it's only false twice, and then I can check here, oh, one of the premises is false, oh, both the premises false. So we never get the true, true, false line. It's always one of the premises false or the conclusion is true. All right. Did I do number, so number 8, Zainab. That one. What's that?
I didn't do it.
You didn't do that one? Yeah, looking at this one, you can say what? It's valid. Can you say that? Yes, because we have a true premise and a false conclusion, but then this is false. We have a true premise and a false conclusion, but then this is false. The rest of the time, either that premise is false or the conclusion is true. So it is a valid argument. I didn't do number 9, but I can tell you that it is valid. How do I know that? A little thing called implication. Number 10. Valid or invalid? Who said that? You are right. Well done. You got to number 10 and it is valid. Yes, because there's only one time when each of these conjunctions is true. This is a disjunction, so it just needs one of them to be true, but that only happens here and here, so here the premises are true. So, I'm sorry, here the conclusion is true, and here the conclusion is true. The only time the premises are both true, the conclusion is true. And this is actually valid by, yeah, here's a question for you. This is false, this is false. What is this logically equivalent to? What's that?
If and only if.
Yes, if and only if, the biconditional. Why is it logically equivalent to the biconditional? Well, it's sort of constructed so that it will be. What do we know about the biconditional? It's true in 2 cases. When is the biconditional true? When they're both true, or when they're both false, which is essentially what this says. It's true when D and E are both true, or when D and E are both false. So this is sort of constructed so that it will be logically equivalent to the biconditional. And the biconditional is if and only if. So, there you go. All right. Well, we've got 15 minutes to go, but here's the thing. I'll let you go early, provided you do one more. Okay? You just have to do this one more. Here it is. Do that one. How many columns would you need?
Is it a pure syllogism or pure hypothetical?
Yeah, I mean, it's not a syllogism, as you
Yeah, there's a few more.
It's pure hypothetical, yes.
64.
Wait a minute. No, how many columns? The uppy-downy ones.
8. 9.
Well, there are 9 of these, but you will also need,
Oh,
you will need 9 more, 1 for each letter, right? So 18 columns. 18 columns, how many rows? No, no. Not 64. What's that?
512.
512, yes. Because, how do you work that out?
It's
Probably because you're a computer nerd. Yes, 2 to the power 9. I know 2 to the power 8 is 256, because that's how many numbers you can convey in a byte, I think. And double that is 512. Yeah, so you better get going, hadn't you? 18 by 512, your table. Perhaps if you put, all right, I won't make you do it. But we have to be able to prove that something like this is valid. And we don't want to have to do a freaking massive table. Wouldn't it be nice if we could, if there was a shortcut method? Oh, there is. Of course, it says so on the syllabus. There is a shortcut method. Well, I've already kind of given hints about what how to take shortcuts previously. Like when I was saying, how many more rows do we have to check? And we didn't have to fill out the whole table. We just had to check. What rows did we have to check? Where the conclusion is false. So in fact, in the shortcut, in the test for validity, what are we looking for? When we make the table, what are we looking for? How many rows are we looking for? Just one. A special row where all the premises are
True.
and the conclusion is
False.
false. All right. What we're going to try and do with the shortcut method is we're going to try and reverse engineer that row. So what we're going to do, the shortcut truth table is going to look like this. Instead of 18 by 512, it's 9 by 1, a bit smaller. Okay? But what we're going to do is, actually there's a good analogy with what you did on your homework. Remember, on your homework, you had two cases where I gave you a long, ugly proposition that might have looked, I don't know, something like this. You know, if P then Q or R, negation of that, if and only if S and T. Something like that, a big ugly proposition. And then I said, I told you, plug in these truth values and work out the truth value of the whole thing. In fact, I only gave you one truth value because you could work it out that way. Right? And that's sort of what we've been doing. You've been taking the truth values of the component propositions and you've been plugging them into longer things and working out the truth value of the long thing. And for every combination of truth values, you've worked out the truth value of the long thing. So that's sort of the bottom up. You start by knowing the truth values of the individual propositions and working out the truth value of the compound proposition. Yeah? Well, we're going to do things in reverse because just like on your homework, there was another one where I gave you something like this, only I told you that the whole thing is, say, true. And then you work backwards to work out the truth values of the component propositions, right? Because I gave you one where there was only one possible way that could make it true if, you know, A was true, B was false, or whatever. That's sort of what we're going to do with the shortcut method. So, we start by making our table. Again, a column for each premise and a column for the conclusion. Double line to show that it's the conclusion. Now, what's the line that, if we made the full table, what was the line we were looking for? Where the premises were all
True.
and the conclusion was false. Okay, so what we're going to do is we're going to make the premises true and the conclusion false. Now, of course, the premises are each compound propositions. So if I make this premise true, where would I write the true? Under the arrow. Now, this is a conditional. How many ways are there for a conditional to be true? 3. So if I started by making this premise true, I would have to look at all 3 possibilities. And actually, I would have to do 3 lines. But I'm lazy. I don't want to have to do 3 lines. So instead of starting by making the premises true, what should I do? Start by making the conclusion false. Why, in this instance, would that only require one line?
Because there's only one way for a conditional to be false.
That's right, because what do we know about conditionals? They can only be false one way. So I write the false under the conditional, and I circle it, because it's the truth value of the whole proposition. And for that to be false, A has to be true, and I has to be false. Yes, because we've memorized our truth table for conditional, and we know that conditionals are only false when the antecedent is true and the consequent is false. All right. Now I know what A. Now I know that if I drew the whole table, the only times the conclusion would be false would be when A is true and I is false. So what else can I fill in immediately? Right, I find where else A is, and it's over here, and I know that it has to be true on this line. And I find where else I is, and it's over here, and I know that it's false. That's going to help me. That's going to mean that I no longer have to do 3 lines to make this premise true. Why? Suppose I want to make this premise true. Why don't I need 3 lines anymore?
It's the only way to make that true is B if B is true.
Yes, because now I know that A is true. The only way for this to be true if A is true is if B is also true. Because if B was false, this would be false. So if B can't be false, it has to be true. So when you're doing the shortcut method, you only ever write a truth value under a letter when there's only one thing it could be. Bless you. If there's more than one thing it could be, then you have to add to the number of lines. If, for example, I started by making this true, then I would have to do 3 separate lines to cover all possibilities. But if you're clever, and this is why the shortcut method requires a little bit of thought. The long method is boring, but you don't really need to think. You just plug in truth values. Here, there's kind of a strategy to it. You're sort of zipping backwards and forwards, only filling in a truth value where there's only one thing it could be. So it's a little bit harder, but it's a little bit more interesting. And it's a lot less work, provided you're smart about it. All right. Now, what can I immediately do? Well, I know that B is true, so I fill in here. Then, I have to make a premise. I'm trying to make all the premises true. Which one should I try next? How about this one? Why? Because if I start with this one, I'll have to do 3 lines. But if I go here, there's only one way for this to be true, which is if C is true. Oh, and look, C is over here, and then if I make this true, D has to be true. You can see there's kind of a domino toppling effect.
How do you know that the whole thing is true? Or how do you know? Or you just guess?
I don't know that it's true. I want to... What I'm doing is saying, look, if I made the giant table for this, right, I would get all kinds of values. Sometimes this would be true, sometimes it would be false, right? But I wouldn't care about the lines where any of the premises are false. Why not? Because I only care about one line. When you make the table, you're looking for the one line where?
All the premises are true and the conclusion is false.
So I'm trying to make that line,
Okay.
right? Now I can't do it by cheating, by just saying, okay, let's make A true and B true here, and then let's make B false. Wait a minute, I can't make B false if I made it true over here. So I have to make it consistent. If A shows up anywhere, it has to be the same truth value wherever it shows up, right? So I'm not just making stuff up. And in fact, that's why I went with this one, because there was only one possible way for this to be false. If A is true and B is false. So I can sort of work out that if I did the big truth table, that would be the only rows I care about when A is true and I is false. Because that would be the only ones where the conclusion is false. And then I plug in A here, and then you can see how it goes. So this will be an actual line on the truth table. And let's see if on the actual line on the truth table, where A is true, B is true, C is true, D is true, E is true, and I is false, let's see if that would make all the premises true and the conclusion false. It's the only line that would make all of these premises true at the same time the conclusion is false. Let's see if it works for the rest of them. What do you think? Will it work?
No.
Why not?
Because I is false.
Because I is false. And why not anyway? Because if it did work, what would that prove? This argument is Invalid. But what do you think? Is this argument invalid? Why not? Because it's a pure hypothetical, right? A leads to B, B leads to C, C leads to D, blah, 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 leads to I, so A leads to I. It's sort of an expanded hypothetical syllogism. It's like lots of hypothetical syllogisms put together. So it's pretty obviously valid. So we're going to fail at some point. We're trying to show that it's invalid, but it isn't. So the argument won't let us do that, because if we actually made the giant table, there wouldn't be a line where all the premises are true and the conclusion is false. So in trying to do this, we're going to fail. Let's see where it happens. Some of you have already worked out where it happens. So I'm making this true. The only way to make this true when E is true is if F is true. So F is true. The only way to make this true is if G is true. So G is true. The only way to make this true is if H is true. Wah, wah, wah. What's the problem? I cannot make this premise true. I got so close. I can make the conclusion false at the same time that all these premises are true. But that's not good enough. They have to be all the premises true at the same time that the conclusion is false. And that didn't happen. So, shortcut method, which we'll talk about more, well, I'll talk about in a video form. If you fail, it's valid. If you succeed, it's invalid. One last thing. I started by making the conclusion false. And that told me that A was true and I was false. Right? So, let's see. Like this. Right? Now, I then went to this one next, because there was only one way that could be true. Where else could I have gone? To this one. There's only one way that this could be true. Which is if what? If H is false. And then I could work backwards. And if I did it that way, where would I hit my snag? I would get this far. So I would manage to make all of these true, but then it would be false here. Okay? So what does that show? Two different tables. Does that mean one's right and the other one's wrong? No. Because there's two different ways to do this. Just because once you made the conclusion false, you can either start on this one or you can start on this one. But either table is correct. Because in both cases I've shown that it's impossible to make all the premises true and the conclusion false. Okay? Alright, now you may go. And don't forget, there will be a homework next Tuesday, and I will see you in cyberspace.